Hello. First of all, to get things out of the way, I'm not an expert in color. Everything that you will see is something that I have learned over the last few years working in color measurements as part of the quality management system in LMS. My basic background is metallurgical and materials engineering. So please, at the end of the presentation, feel free to correct any minor scientific inaccuracies that might be in the presentation. The second is the title that you see on the slide is slightly different from what was announced. It's just a little bit more elaborate. I would like to be talking about issues in relating color measurements of high gloss metallic surfaces to visual perception of color. Why is this important? Because reproducibility of color is an indicator of quality in the industry. And in order to be able to do that, we need to measure and constantly control the color that goes on onto our products. And why is this important? Because think about it, when you buy a bag for 20,000 euros and you have two buckles on each side, they better be of the same color because otherwise you feel like you're being cheated. Not only that, internally, we need to be able to be sure that 50, 100 years down the line, when we produce new materials, they will still be of the same quality as what was imagined previously. So this question of measuring color and controlling color is very important. What my presentation will try to add a little bit in terms of the previous presentations that we just had in terms of the basic physics behind the appearance and the measurement of color is the visual perception aspect, because as we all know, we all look at colors differently. Our eyes are not the same. And so there is a huge biological factor that figures in when we talk about quality control of color, which also needs to be taken into account when we work in the industry. So this is why I chose to share this subject with you. So let's get it started directly. We can start with the characterization of color. A little over 50 years ago, the Comité International d'Éclairage defined a three-dimensional representation of color using the LAB axis, where you have the L axis, which talks just simply about what they call the lightness, which ranges from a 0, which is 100% pure black, to 100, which is 100% purely reflective white surface or colorless surface. And you have the A and the B axes, which represent what we call chromaticity and hues. A being the red-green axis, and B being the yellow-blue axis. And based on these coordinates, we could talk about variation in colors using vectorial coordinates very simply. So you can talk about two different colors, L1, A1, B1, L2, A2, B2, and the difference in the vectorial coordinates in a rectilinear space would actually represent the variation in linear coordinates. The problem is when they described this model and once they started trying to apply it, they realized that visual perception does not directly vary linearly as we would have mathematical models to believe in this kind of representation. So they chose to move in order to be more coherent with the human eye to polar coordinates, which they seemed were better associated with the visual perception of color. So instead of talking about LAB, we talk about LCH, where C is basically the radial distance or the chromaticity. When we have C closer to the L axis, we basically have achromatic colors. And the further we move away from the L axis, we have more solid, saturated colors. And the other parameter is the angle, which is H, which is the hue, which basically defines the variation between the red to the yellow to the green to the blue. So moving in this direction actually permits us to be slightly closer to the way the human eye perceives colors, and the variations in CH are closer to variations observable by the human eye. And once we have ways of characterizing color, we can talk about characterizing color differences. The first formula was the simplest mathematical three-dimensional geometry formula that you can see. You have two colors, L1, A1, B1, L2, A2, B2. And you just take the vectorial difference between the two, which was called the CIE 76 formula. So very, very simple mathematics. And if we talk about tolerances, saying a delta of less than this much is something that is perceptible, what you get in simple coordinates is a screen. And at this point, they talk about a value of 2.3 being the minimum perceptible difference for the human eye. This is something that is debatable because the human eye does not actually distinguish 2.3 in all the three-dimensional coordinates in which the color is represented, which is why there was a difference between the calculated differences and the perceived differences, and they had to evolve the formula based out of visual perception studies. So through the 70s, they did a lot of studies with over 2,000 textile samples with different colors, where they actually brought in mathematical models to substantiate what was observed by the visual perception studies to the changes that were perceptible or imperceptible, and which is what gave birth to the CMC-LC formula, where basically what they did is they took the LCH coordinates, they added correction factors, the little l, the little c, and they tried to kind of normalize the variations that are perceptible or imperceptible along the three axes, because basically the human eye doesn't respond the same way to variations in L or to variations in H or to variations in C. And what happens is when we use different kinds of constants, instead of having a sphere as before, we now have ellipses. And these are easier to model and manipulate, and are even further closer to actual perceivable differences in terms of the human eye. So this delta ECMC, as we will be addressing it henceforth, is one of the most standard ways of measuring color differences, typically in the textile industry. So what does this mean? How do we create the tolerance using the CMC formula? Is basically for low gloss materials, typically textiles, we use the constants L is equal to 2 and C is equal to 1. This translates to ellipses of this sort in the LCH coordinates. And basically, if you take a section of the plane, what you see are varying size of ellipses. You see that closer to the L axis, the ellipses are tiny, and farther off, they're much bigger. What does this mean? This means that the closer we get to achromatic colors, the eye is more and more sensitive. So you tolerate lesser any small variations, as opposed to when you go further off and you go towards the edges, where we can have a variation in the measurement and the eye still won't be able to see it. So less than 1 in this kind of a delta E measurement is generally considered as visually imperceptible. And what does this mean along the L axis though, because we only see a section? This basically translates to the same size of ellipses along the L axis as well. And this is a major limitation, because do these simple correction factors actually apply to high gloss materials? So this is a very, very important question that seems to be a little bit dispersed in terms of scientific opinion. Just to wind up the history of tolerances and color differences, we had further studies which kind of made more elaborate models, like the CIE94 formula, where I had correction factors for LC and H, which is very close to the delta ECMC, or further with the TIE 2000 formula, where they went even further with a more elaborate corrective factor, which was to include mixtures of pigments in paints and compensate for chemical variations based off of it. So basically, we increase the complexity of models to get closer and closer to what the human eye can see. Let's come back to our metallic surfaces. So basically, using LAV for metallic surfaces was applied right away, right from when the LED system was invented. We have studies from the 70s and 80s which clearly describe variations of color in ternary, copper, gold, and silver alloys, talking about the LAV coordinates for each composition. And since there's nothing new, we also know that there were studies that were done which tried to understand how the way the human eye perceives these colors for metallic surfaces affects the way we tolerate color differences or not. So this study, for example, uses an indirect lighting with the window behind the observer and changes the angle of the metallic plates that are being compared in the quality control in the automobile industry. And basically, they try to see what are the LNC correction factors in the CMC formula based off of the angle of the orientation of the samples. We previously talked about 2 and 1 as the LNC factors for the textiles. And this study showed that for certain angles, the factors can be as far as 2 and 3. So what does this mean? This means that basically we need a lot of research in order to be able to find mathematical formulae for creating tolerances for high gloss metallic surfaces when we talk about that pure innate color. So what other industries did, the jewelry industry, for example, was to simply base off of visual perception studies for white gold, and they defined tolerances for what they considered to be good white, reasonably white, off-white, and so on. And they used CI lab measurements in order to quantify this. But they don't talk about texture, and further off, they don't talk about any other alloys than white gold. And as far as the automobile industry is concerned, for example, they also did a bit of research on how best to define tolerances. And they found that basically all formulas more or less equivalent starting from the CMC. But they mentioned that visual tolerances will always, visual perception studies will always have to accompany any mathematical models because they believe that we're just not sufficiently advanced with these mathematical models as of date. So what does this mean is that tolerances for quality control of metallic surfaces depends not just on the color of the metal itself, but also on the observation conditions and also on the surface of these metals. And these vary heavily from existing standards that are actually based on low reflective surfaces such as textiles. So what we did was to take a case study and look at what tolerances we could apply for our yellow gold coatings in our industry. We said, look, everybody uses delta ECMC less than 1.1 for visually perceptible color changes. So let's try with that. So we took the formula, we asked ourselves the question, how well does this model actually match visual perceptions? And in order to do that, we basically had visual observation studies where we had a panelist that looked at these samples with D65 lighting, indirect reflection within a light chamber. We did LAV measurements with the spectropolarimeter, which gives us the LCH coordinates for each of these samples. And we had data models that helped us to try and see how we can match what was seen in the visual perception studies with the measurements and see what model best correlates between what's measured, what's observed. To give you a brief idea, 3 campaigns were done, 19 panelists, more than 40 different samples from 4 different suppliers, just go all the way out, and 3 different data models. In very brief, let's look at what the tolerance model gave us. The first model we applied was very simple. We said, we use delta ECMC less than 1.1. How far does it correlate with the visual perception studies? As you can see in this little graph here, on this axis, what you see are basically the results of the visual perception studies, and the color coding is basically from the CMC measurements. You see from what people consider to be okay, there are quite a few samples that were measurement-wise not okay, and vice versa. Samples that were considered not okay by the panelists, there were a few of them that were measurement-wise okay. And when we look at the statistics over this model, we basically see that there's about a 57% match between the calculated tolerances and the visual perception. Clearly not the best model to be applied directly in quality control. Starting with this, we can only do better. Second model was to use a mathematical model that is created by the application from data color that actually proposes to correlate visual perception data and their measurements in order to create a sort of three-dimensional space that kind of is the best fit between the 2 data sets. So when we look at this model that was statistically generated by the data color app, we're a little bit better. 69% match between the data colors model and our visual perception evaluations. We're already going in the right direction. Little better. And what we did on the side was to use simple data visualization and see how we can try and correlate individual parameters in order to rely, instead of relying on delta E measurements. We said, let's forget delta E. We'll look at delta L, delta C, delta H individually and see if we are able to correlate tolerances between these 3 and what the people actually saw in these visual perception studies. And here, surprisingly, we were able to get up to 85% of a match between what the visual perception studies showed and what the measurements showed. Which is very interesting overall, because it seems like we can make simple mathematical models for tolerances, at least in this particular case, instead of going for complex mathematical family tolerances. In summary, because this is an ongoing work, this is really fresh work, the delta CMC models are not directly applicable, at least in our case, for creating tolerances for the color evaluation of metallic objects. But when we try to use data correlation between observations and measurements, we find that correlated tolerances can be quite interesting. And when we go one step further, what we derived out of this little study was that large differences in the L-axis can be relatively imperceptible, and people are more sensitive to variations in hues, basically the angle, than variations along the radial coordinate, which is the chromaticity, which is very interesting because this correlates very well with previous studies of human perception of color. Upcoming work, and this is still something that we need to look at, is how repeatable are these panelists? How reproducible are these observations in terms of reproducibility over batches of production? How do we define a gray zone? Because tolerance cannot just be a simple line. There has to be a gray zone around it in order to talk about what is in between. What influence do the observation conditions have? And this is a huge question. We saw in the previous studies that observation conditions can vary in a very substantial way the way people look at colors. And also, how do we make sure that these conditions that we find finally are not overly strict? Because we can have tolerances that can be very strict, and it should not for all that translate into 50% pieces, especially if they are not perceptible. So how do we make sure that we're not going over as well? And finally, the open questions that we have is, once we have these kinds of models, how do we apply these to other gold? We talked about yellow gold. What about rose gold? Are the tolerances similar? Are they different? How different? What about other textures? When we go from a bright polished surface to a brushed surface, how do these tolerances vary? And what about other geometries? Geometries where it's difficult to measure the color. How do you go about creating tolerances for such pieces? And these are more open questions to the public, because I think you all have more experiences in color than I have. What factors are important to take into consideration when doing visual perception studies, whether it be illumination or the angle of incidence? And is, by any chance, the DIN 99 another way of characterizing color that we didn't talk about? Is it a better standard for qualifying materials? And any other ideas are also, of course, very important. And I thank you for your attention.